I'm going to start recording this session. I'm gonna do it locally, and then I'm gonna upload it to YouTube because I want to have as much quality as I can. Okay, so I will send you the YouTube link for that later today. But for now, the first thing that you need is to have the handout with you, and also I'm going to share a presentation through the chat. I want you to download that. Okay. Make sure that you download it, and I'm gonna start by sharing it on Zoom. Okay. So I just wanna. Is everybody able to see the presentation? Lab 2, quantifying electrical energy.
Yep, I see it.
Okay, thank you. So we're gonna do a quick review of the setup that we're gonna have for today. So the first one is gonna focus solely on the oscilloscope. We're gonna be adjusting the vertical controls for channel 1 and the horizontal controls again. Okay, so that's very straightforward. Then so I'm gonna stop here, and once we have done assignment number 1, we're gonna come back to the presentation. Okay, so for now, before we start paying attention to the Zoom video, I'm gonna need you to either, for example, you can take the mouse and right click on any person that doesn't have a video. Okay, for example, right now I'm gonna right click on Ryan. Ryan's like thumbnail, like Zoom thumbnail, and then I'm gonna click on hide non-participant video. No, hide non-video participants. In that way, you're gonna hide all the red, all the black squares with the names on it, and then you will only see my video from Jesus Reyes Blanco, where you have the oscilloscope, and then the other video from Jay Blanco. Please let me know if you were able to set it that way. Also, you can choose to have the gallery view. Right now, if you have the 2 videos at the top, that means that you have the presenter view or speaker view. But also you can choose to have the gallery view. In that way, you're gonna have 2 videos side to side, and you will have on the top center of the screen, you will see total non-video participants that should be equal to 11. Was everybody able to do that? For example, right now, I am in gallery view, and I only have 2 videos. I have the oscilloscope on one, and I have the pyramid of instruments on the other one. And I would like you to have the same view, but you have to set it up from your end. So now that you do, whenever you hover over the video, each video, you're gonna see, for example, I'm gonna hover over my the pyramid of instruments, and you're gonna see at the top right corner the 3 dots. If you click on those 3 dots, you're gonna see you look for the pin video option. When you do, then the only thing that you will see, and I would recommend you to have it on full screen. Okay. The only thing that you will see is the pyramid of instruments. Okay, you can go back again if you on the top right corner. If you click on gallery view, you go back to the two videos side to side. Is everybody comfortable on navigating through Zoom with these 2 videos?
Yes.
Thank you. So right now, if you do thumbs up, I will not be able to see it. But if you reply on the chat to my questions, we're gonna be able to see it. Okay. So we're gonna start by setting up the oscilloscope. So right now, I'm gonna ask you to pin the video feed of the oscilloscope. Okay, in that way you're gonna see it. And right now, I'm gonna show you that we're gonna go over the steps. So right now I have my handout, and it says the initialization of the oscilloscope is required to set the instrument to a point from which all measurements can be referenced. The oscilloscope is going to be a reference, okay? The following procedure should be used when the oscilloscope is used to quantify signals generated from transducers, okay? Transducers could be sensors, could be instruments, whatever is providing a voltage output, okay? So we're gonna start with the procedure. We're gonna turn on the oscilloscope. If you see my finger over here, the switch is over here. It's already on. And number two, a previous configuration may be loaded. Load its default setup by pressing default setup button. You don't see it right there because if I move the oscilloscope, I'm gonna lose the focus on the bottom of the screen, and I don't wanna do that. So what I'm going to do, I'm just gonna press the default setting. And here on the bottom left corner, you can see default setup recall. Okay, so that's step two. Now let's do a step three. Can somebody help me with a step three? If you can read it from your end. Who would like to volunteer, or should I make someone volunteer? It will be fun to hear
I can do it.
somebody else too. Okay, yeah, please.
So within the vertical system control, push the yellow button 1 to bring the channel 1 setup menu up.
Mhm.
And
So
then
yeah, go ahead, keep going.
yep, and then press the probe 10x voltage button.
Keep going. Yep.
Then press the attenuation 10x button
Yes.
by using the multi-purpose knob, changing the attenuation factor to 1x.
Thank you. Can you just take me through the end of the assignment? We're almost there. If you
Yeah,
can do number 4.
then
Thank you.
set the vertical scale to 5 volts per DIV.
5 volts. You can see 5 volts at the top, at the bottom left right here. That's where the vertical scale is. And what is step 5?
In the horizontal scale to 5 ms.
Okay, so now with the horizontal control, I'm gonna move it to 5 millivolts right there. So I'm gonna try to make the camera to focus on that. Okay, so here in the bottom, in the bottom center of the screen, you'll see 5 millivolts. Okay, so that's for the horizontal scale. And at the bottom left corner, you see 5 volts in yellow. So right now, the oscilloscope has been initiated. Okay, now we're gonna move on to assignment 2. So I'm gonna go back to the PowerPoint presentation. Okay. Okay, PowerPoint presentation. And we're gonna start with, move on to assignment 2. Here, we're gonna have the function generator, okay, on the left. we're gonna have it connected using a T connector to channel number 1 on the oscilloscope, and then we're gonna be connecting it to the multimeter. Okay, now I'm gonna show you the video feed for the instrument. I'm gonna go back. So I'm gonna go to gallery view, and now I wanna pin the video on the pyramid. Okay. So at this point, you can see we have the function generator, we have the multimeter, and on the other video, we have the oscilloscope. Now, this cable is connected to a T connector right there. And that T connector has a cable going to the multimeter. And right here, I'm gonna set it to voltage RMS. Remember, everything coming from the multimeter is gonna be a signal, a quantity RMS. For this experiment, we're gonna be switching from voltage RMS with this button at the bottom left corner, and also the frequency. Okay, we're gonna be toggling between frequency option and voltage RMS option for AC signal. So I'm gonna turn on the function generator. Okay, and right now the function generator is set to output RMS signal of 1.69 volts RMS. Okay, so as you can see there, 1.69. You don't have to write that down just yet. And then I'm going to connect one of the cables coming from the function generator to the oscilloscope, and we're gonna see what happens. Okay. Now, if you want to go to gallery view on your end, in that way you're gonna see one video of the instruments and the other one from the oscilloscope. Can we see the shape of a sine wave on the oscilloscope?
Yes.
Yep.
Yep, awesome. So at this point, you can see that the oscilloscope, the sine wave that is being generated by the function generator, you can visualize it on the oscilloscope, and you can see that the peaks of that sine wave are not going beyond the main division of the oscilloscope right here. So this means that between the 0 axis, the horizontal axis right here, and the second and the first division, main division, that means 5 volts. Okay, so right now it is around half of that, so it's around 2.5 volts peak. Okay, if I were to increase the output from the function generator to make sure I have 5 volts peak, okay, it will be something like this. Now you can see that the peak of the sine wave is crossing one of the main, all the peaks, the negatives and the positive peaks are crossing almost the divisions for each side of the sine wave. Okay, so now we're gonna go through the procedure. Okay, so on step number 1, okay, let me read the description for assignment 2 first. We're gonna have a digital multimeter, which is the one with the numbers, okay, with the little screen with the numbers, can be used to measure current, resistance, and the voltage of a signal. When an AC signal is recorded, the multimeter displays the root mean square value, okay? So right now, what you're seeing on the multimeter, right here, that's the root mean square value, okay? The oscilloscope is capable of measuring voltage only. This one, because it's more advanced, you're able to set it to current too. However, unlike the multimeter, the oscilloscope displays, okay, this is the keyword, displays the signal of a TFT display, allowing the period and the frequency of the signal to be calculated. Okay, period. You're gonna see that we have the vertical divisions right here, and each vertical division time-wise is worth 5 milliseconds. Okay. So right now we haven't adjusted the frequency of the sine wave. Now, we're gonna start with the procedure. Here, the step number 1 is already taken care of, but we're gonna go over that. So Ryan, can you help me with step number 1, assignment 2, please?
Wait, do you want me to just like read it?
Yeah, just read it out loud, please. Yes.
Okay, figure 1 shows the proper equipment configuration. The output of the function generator will be the input of the oscilloscope and multimeter. Connect the function generator to the oscilloscope channel 1.
Awesome. Now, all of that is already set. Would you mind continuing on step number 2 and read the whole thing, please?
Okay. Turn the function generator on. Set the function generator to an output of 100 hertz sine wave at the maximum amplitude.
And can you read the important note?
Oh yeah, important. Yeah, important. Whenever you generate a new signal, use a multimeter and oscilloscope to check the magnitude and frequency of your waveform. Note that the multimeter outputs RMS voltage for an AC signal.
Awesome, thank you. So right now the objective is to create, and at this point, from this point on, you should start taking notes. Okay, I can suggest you to have a spreadsheet ready so you can start taking notes on that. Or if you want to use a Word file, that works too. So I'm going to set the function generator. I'm gonna modify the frequency, okay? And I'm gonna set it to 100 hertz. If you take a look to the multimeter, I'm gonna use the frequency option on the multimeter, and it's telling me that I am at 62.99 hertz. So I need to regulate the frequency, okay, and reach 100 hertz. So as I increase the multiplier on the function generator, you were able to see that my signal, the period of my signal was being shortened, okay? So right now, the frequency is around 114 hertz. Please write that down. So that will be assignment 2, step 2, 114 hertz. Now let's check the voltage on this signal. So I'm gonna do voltage AC. And if you take a look on the multimeter, we have 3.8 volts RMS, but step 2 is saying that we want to have it at a maximum amplitude. So I'm gonna crank up the output level knob all the way, okay? Now, we have the right frequency at 113 hertz, and we have the voltage RMS, and please write this down, 8.09 volts RMS. Okay, so that's the end of step 2. We need to set for step number 3, and I'm gonna read the whole step. Set the oscilloscope channel 1 coupling to AC. Press the yellow button 1, go to coupling DC menu, and use the multi-purpose knob to select AC. Adjust the vertical and horizontal scale knobs to have at least one complete cycle on the screen. If you take a look at the oscilloscope right now, that we have at least one complete cycle. Actually, we have like around 3 at least, okay? So if you take a look to the oscilloscope, I'm going to press button number 1, and I'm gonna change the coupling to, right now it is set to DC. I'm gonna change it to AC. Okay. If you remember, DC coupling lets AC and DC components of a signals through. Once I activated the DC coupling, sorry, the AC coupling, you didn't see much difference on the oscilloscope. Why? Because the DC component of the initial signal was really, really close to 0. Okay. So it's already set to AC coupling. Right now, I'm gonna save us some time, and the oscilloscope has an option called auto set. Okay. When you press auto set, and I'm gonna do it right now, when you press auto set, it's gonna calculate. So you saw the screen moving a little bit. You're gonna be able to have the oscilloscope calculate different parameters for you. Okay. So at this point, the first two numbers that we wrote down, those were coming from the multimeter. And please make a note on that. So it was 114 hertz read from the multimeter and 8.08 volts RMS. Make a note that those values are coming from the multimeter, because all the signals that are gonna be generating, we need to make the distinction between them. Okay. So now, from the oscilloscope, and you're gonna write this down, all these values down. We have a peak-to-peak value of 23.4. Again, a peak-to-peak value of 23.4 volts. We have a period of 9.98 milliseconds. Make it 10 milliseconds. Just is switching right here. And an RMS value of 8.14 volts RMS. And also the frequency coming from the oscilloscope is 100.0 hertz. Those are the values that you need to write down. Okay. Are we ready to go?
Sorry, what was that last part you said?
For frequency or voltage RMS?
Frequency.
100 on the dot. 100 hertz.
And the unit for the period, is that milliseconds?
Milliseconds, yes.
Okay.
Mm-hmm.
I'm sorry, did you give us the VP, so like voltage peak number?
So because I gave you the voltage peak to peak.
Oh,
remember,
right.
yeah,
Divide
that
by
you can calculate it for that, just divided by 2.
Right.
Mm-hmm. And what we just did, that was a step 4 of the procedure. Okay, so I'm gonna read it out loud. Observe the signal with the digital multimeter and oscilloscope. Record voltage peak, voltage peak to peak, voltage RMS, and the period of the signal. You can tell that the multimeter doesn't have a screen, okay? But for the final report, you will have to convert the voltage RMS from the multimeter into voltage peak and voltage peak to peak, because you want to compare the values obtained from the multimeter to the values obtained from the oscilloscope. Okay. Now, Ryan, I'm gonna keep bugging you. If you can help me with step number 5.
Okay. Adjust the amplitude on the function generator to an output of 5 volts RMS and 100 hertz. Sine wave. Record the V peak to volts peak to peak and the volt peak volt RMS and period.
Awesome. So we're gonna acquire all the data from the instrument, but now we need to set a new wave. I'm gonna go to the function generator and I'm gonna modify the output. So right now it is at 8 volts RMS. I'm gonna decrease that output to 5 RMS. Okay, and I'm gonna make sure that I have the right frequency. Okay, close enough. Now, for step number 5, you're gonna write down data from multimeter. We have 99.91 hertz, and we have an amplitude of 5.00 volts RMS. Those are coming from the multimeter. That's the raw data. Now, from the oscilloscope, I'm gonna do the auto set again, and you're gonna see the screen change, okay? So now the oscilloscope decrease the scale, decrease the vertical scale. That's why now the whole sine wave is occupying the entire screen. But and now these values are gonna be coming from the oscilloscope, okay? We're gonna start with voltage peak to peak. That's equal to 14.4 volts peak to peak, okay? Now for the period, we have 10 milliseconds as well. For RMS, we have 5.03. And for frequency, we have 100 hertz. I'm gonna repeat the values again from the top, from the oscilloscope. Peak to peak voltage is equal to 14.4. Period is equal to 10 milliseconds. Voltage RMS is equal to 5.02. And frequency is equal to 100 hertz. Okay, if we are ready to go, Ryan, this last step for assignment 2, please, if you can help us.
Yeah. Set the function generator output frequency to 10,000 hertz. Record the voltage peak to peak, the voltage peak, and the voltage RMS, and the period.
Thank you. So here, we're gonna keep the same amplitude from before, those 5 volts RMS. The only thing that we are modifying is the frequency. I'm gonna go to the function generator and I'm gonna switch the range. Right now on the function generator, I am at the range of the hundreds. Then if I go one to the right, that's thousands. And this is 10 to the 3 or 20K. So I'm gonna press that. I'm going to check the frequency using the multimeter. And right now it says 10.01 kilohertz. I'm gonna leave it like that. And on the oscilloscope, I'm gonna press the auto set button. So it helps me to properly measure that signal. Now we start recording. Now this is step 6. And these are the parameters coming from the multimeter. We have 10,000 and 10 hertz. And for the voltage, we have 5.03 volts RMS. Again, frequency, 10,000 and 10 hertz. And voltage, we have 5.03 volts RMS. Now for the oscilloscope. For the oscilloscope, we have a voltage peak of a voltage peak of 14.7. Sorry, that's peak to peak, okay? 14.7, a period of 100 microseconds. Again, a period of 100 microseconds. Then a voltage RMS of 5.07 volts RMS and a frequency of 10,000 hertz. These four parameters were coming from the oscilloscope. I'm gonna repeat them. Voltage peak to peak, 14.7 volts. Period, 100 microseconds. Voltage RMS is equal to 5.7. I don't know if it was 0.04 the first time that I read it. Okay, but either or is gonna be fine. And frequency is equal to 10,000 hertz. Did we get those values right? Okay. Now I'm going to, and that was the end of assignment number 2. I'm gonna go back to my PowerPoint presentation, and I'm gonna show you how we're gonna set up for assignment 3. In assignment 3, the 3 instruments that we're gonna use is the oscilloscope at the top, and on channel 1, we're gonna connect one cable coming from the function generator and another cable to channel 2 coming from the power supply. Okay, that's what we're gonna have. So right now I'm going to grab a cable. I'm gonna connect to the power supply. I'm gonna turn on the power supply. And I'm going to connect the second cable to the second channel of the oscilloscope. So if you take a look to the pyramid at the very top, this guy is set to 7.4 volts. You also can see a second LED screen where you can also generate current. So you see amps here. And the top row, that's to regulate the current. And the bottom row is to regulate the voltage. For this assignment, we have to have 10 volts. So might as well just gonna set it 10 volts right there. Okay, and just a little bit more. So we have 10 volts on the power supply or the second channel of the oscilloscope. Okay, so I'm going to read out loud the description for assignment 3. So it says, in assignment 2, the digital multimeter was used to quantify the amplitude of an AC signal. In order to quantify a DC signal, the multimeter AC-DC switch must be set to DC. The oscilloscope is capable of measuring 2 simultaneous signals. Each signal can be comprised of an AC and DC component. If only the AC component of the signal is to be monitored, the oscilloscope should be set to AC coupling. If both the AC and DC components of the signals are desired, the oscilloscope should be set to DC coupling. The objective of this assignment is to introduce to channel analysis using the oscilloscope and examine the effects of AC-DC coupling. Okay. And I'm gonna just read the important note. Whenever you generate a new signal, use the multimeter and oscilloscope to check the magnitude and frequency of your waveform. You may need to disconnect your cables from the oscilloscope in order to use the multimeter, because as I show you on the presentation on the slide for assignment 3, we don't have the multimeter anymore. Okay, but we'll figure it out with the oscilloscope. Now we already have. If you take a look to the block diagram or figure number 2, we already have everything connected. So we're gonna start with assignment 3, step 2. Would like someone to help me with this assignment, please?
Yeah, I can do it.
Thank you, Henry. Go ahead, please.
Turn on channel 2 by pressing the blue button 2. If this is off, this will allow channels 1 and 2 to be viewed simultaneously.
Okay, so I'm gonna press number 2 right now. So if you take a look to the oscilloscope, you'll see my finger on top of the blue button. And as soon as I did, you were able to see at the bottom this blue legend that indicates that the channel number 2 is on. Okay, and it has a scale of 500 millivolts. At this point, I'm going to change the attenuation the same way we did it for channel 1 at the very beginning. Okay. Now, would you mind continuing at step 3, please?
Set the output of the function generator to 5 volts RMS at 1000 hertz.
Okay, I'm gonna go to the function generator and I'm going to set it to 5 volts RMS, which we already have on the multimeter. And I just need to modify the frequency. Right now it is at 10,000 hertz. So on the function generator, I'm gonna go order of magnitude less. And right now my multimeter is at 1100 hertz-ish. I'm going to decrease that to 1000 hertz. Almost there. Okay, close enough. And now, so we have the proper signal. Can you do 4, please?
Adjust the vertical scale of channel 2 to 5 volts per division.
Yes. Can you do 5?
Yep. Set the oscilloscope channel 2 coupling to DC. Press the blue button 2, go to coupling DC menu, and use the multi-purpose knob to select DC if it was not selected before.
So I'm gonna do on the oscilloscope, menu 2, and the DC coupling is on as of now. Okay. Please continue.
Adjust the output voltage from the power supply to 10 volts.
So if you take a look to the pyramid, you will see that we already have it set up at 10 volts. Okay.
Record the voltage peak to peak, voltage RMS, and periods associated with channels 1 and 2.
So right now, let's analyze what we have on the oscilloscope. It's just like I'm seeing something that it is not letting the signal to be completely locked down. It's better now. Okay. So right now I'm just gonna adjust the time scale on the oscilloscope, and we can see both signals at the same time, okay? The yellow one is coming from channel number 1 or the function generator, and the blue one or the line with the zero slope line is the blue one at the top, okay? If you remember, the vertical division on channel 2 is equal to 5 volts, okay? So as you can see, this is the first division, and this is the second division. So we have 2 divisions times 5 volts. Our DC signal, it is right here, okay? We are able to see it because the DC coupling is on. The next step says set the AC coupling on channel 2, and that's what I'm going to do. Were you able to see that it went from 10 volts to 0 volts? I'm gonna do it again. I'm gonna go back to DC coupling on channel 2. At this point, I would like you to focus on the oscilloscope, okay? And I'm gonna, right now, channel 2 has DC coupling on. I'm gonna switch it back to AC coupling. Do you guys see that? How it went down to the 0 line?
Yep.
Yeah.
Okay, thank you. So at this point, I'm gonna do it again. And I think the frequency for our sine wave is a little bit off. I just wanna adjust it a little bit because we need to take some measurements here. Okay. So right now, we're gonna record the values that the step 7 is requiring. So let's do it for channel number 1. So on column 1, you're gonna have channel number 1, and I'm gonna read out loud the values. We have voltage peak to peak equal to 14.6. We have a period of 1.0 milliseconds. We have an RMS value of 5.06 volts and a frequency of 961 hertz. I'm gonna repeat them again. For channel number 1 or column 1 of your on your logbook or a spreadsheet or whichever you are using, whatever you're using to take notes, we have voltage peak of 14.6, peak to peak, my bad, voltage peak to peak. We have a period of 1.04 milliseconds. We have a voltage RMS of 5.4, and we have a frequency of 959 hertz.
You said 5.4 VRMS.
Volts RMS, yes. Now, for channel number 2, our DC signal, as you can see, it doesn't have a shape. So trying to quantify voltage peak or voltage peak to peak is not applicable because those quantities are related to a shape. The only thing that you can quantify for a DC signal is voltage RMS. The voltage RMS is going to be the same as the amplitude of your DC signal. In this case, what is the amplitude of our DC signal?
Is it 0 there?
Good, excellent point. So right now it looks like the blue line, well, the blue line is indeed on top of the 0 line, okay? But when I pressed the auto set button on the oscilloscope is sharing the full screen with two signals. So it decided to set the 0 of the center of the signal to the second, to this vertical division. So this is the 0 of channel 2. So if this is 0, I go to the next one. That will be 5 volts. And if I go to the next one, that will be 10 volts. Okay. Right now, I'm going to center the signal to be aligned with the 0 axis of the screen right there. And I'm going to do the same for the sine wave. Okay. Now, both channels are centered. Okay. So what is the amplitude of the DC signal? It is 10. So voltage RMS is equal to 10 volts for channel number 2. What about the period of that DC signal? Can we calculate the period?
Yeah.
For the DC signal?
Oh, if we're not, are we given a frequency there? Kind of blurry.
So we are focusing on the blue signal, okay? And this is a question in general, do DC signals vary through time?
No.
That is correct. If the signal doesn't vary through time, a period cannot be calculated, and therefore you cannot get the reciprocal of the period, which is the frequency, right? So it is not applicable. Period and frequency are not applicable for this DC signal. At this point, remember that the only parameter that you need to define a DC signal, a voltage DC, is the amplitude. In this case, that will be the RMS value equals to 10 Hertz. So right now, if we were to convert 5 volts RMS to voltage peak for channel number 1 or for the AC signal, what will be the result of that operation?
Say that one more time.
If we were to convert 5 volts RMS to voltage peak, how do we do that? And this is very important to remember. You have to take the voltage RMS, in this case is 5 volts. You have to take that and divide it by the magic number. What is the magic number?
0.707.
0.707. So take that 5 and divide it by 0.707. You will get around So if you take out your calculator real quick, 5 divided by 0.707, you get 7.07 for voltage peak. If you take a look to the oscilloscope, the yellow signal, you can see that the yellow signal is going beyond the first division. And that first division means 5 volts. So it's going above the subdivision. In this case, the subdivision is worth 1. So it goes beyond that guy and that guy. So it's around 7 volts peak. So I want to bring up.
You're saying that's for the DC signal?
This is for AC signal.
AC signal. Okay.
AC signal for the yellow, for the sine wave.
Got it.
Okay. So I would like to bring up the summary that we did on Tuesday. So let me share it. The important definition slide. Okay. What we use is this conversion. Okay. This is the fundamental relationship that you're going to be using a lot in the lab. So make sure that you remember voltage RMS is equal to or proportional to the peak, voltage peak, or being multiplied by the magic number 0.707. So right now you wanted to find the voltage peak. So you send the 0.707 divided to the other side of the equation to get voltage peak equal to voltage RMS divided by 0.707. Any questions for this relationship?
Because we were supposed to be recording the voltage peak, you could also get that from dividing the peak to peak voltage, right?
By 2, correct, yes.
So what if those two numbers are different?
By how much?
Oh, well, for example, on the channel 1, we have the voltage peak to peak as 14.6. So that's the voltage peak should be 7.3.
Yep.
But then the voltage RMS was 5.4 volts RMS, and that divided by the magic number is 7.637.
Correct. So that's a great point, and that's part of the lab, because they are different instruments. They have different resistors, different capacitors. One is the multimeter is slightly older than the oscilloscope and all that. So between instruments, you're gonna see different quantities, but the difference shouldn't be more than 5%. Otherwise, there's probably something wrong. Does that make sense?
Yes.
Okay, so we have a comment on the chat. We have Marcus saying magic number is a little larger than 0.707, rounding and difference in instruments. The magic number is just the first 3 significant digits of the ratio of 1 over the square root of 2. If you want the full number, is that 1 over the square root of 2.
Yeah, I think he was trying to explain to me why the number would be slightly different.
Yeah, exactly. That's all. We'll just, yeah.
Cool. So so that's the end of assignment number 3. Are we good to start with assignment number 4?
Yeah.
Okie doke. So I'm going to cancel the spotlight video. Okay, good. So I'm gonna start with the introduction on, let me bring up let me share the diagram for assignment number 4. Okay, so here we go. And I'm gonna read it out loud. The multimeter, bottom right, can be used to measure the RMS voltage of a signal, but it has an upper usable frequency called the 3 dB down point. The 3 dB down point is defined as the frequency at which the measured voltage, or VO, drops to the magic number, or that relationship, 1 over the square root of 2 of the actual input voltage, VI, period. If you take a look to the slide, you can see that the oscilloscope is going to be our voltage input, and the multimeter is going to be our voltage output. I'm going to continue reading. The 3 dB down point will be determined by generating a sinusoidal wave at a constant amplitude with the function generator. The amplitude of the signal will be recorded with the multimeter and oscilloscope at various frequencies. So the output is going to remain the same throughout this assignment. The only thing that is going to change is the frequency. Remember that amplitude and frequency and shape is being changed from the function generator. I'm going to continue reading. The 3 dB down point can then be determined by plotting the ratio of the measured voltage, V output, to the input voltage, V input, in dB versus log frequency, period. The frequency at which the ratio drops by 3 decibels is the 3 dB down point, also called the cutoff frequency. If you take a look to the slide, the title of this slide is Digital Multimeter Upper Usable Frequency Range. Usable frequency range, we can substitute that by cutoff frequency, okay? That usable frequency range is defined by the 3 dB down point, which is the one that we're gonna calculate. So I'm gonna continue. I just want to read out loud the equation that we have there. So gain dB, or gain decibels, in decibels, is equal to 20 log of 10, log base 10 of the gain. And that gain is just the ratio between the output voltage and the input voltage, okay? Right now in this experiment, we're just gonna quantify output and input. So I'm gonna start with step number 1. Equipment configuration will be identical to assignment number 2. At this point, I'm going to disconnect channel 2 from the oscilloscope. I'm gonna turn off the power supply, the DC power supply, okay. And I'm gonna make sure that I have the function generator connected to the multimeter, and the multimeter connected to the function generator. So we are good there. Oh, there's a cable in the way. Okay, that's better. Now, would someone would like to volunteer for this assignment? The steps are short, but we're gonna be collecting many data points.
I can do it.
Awesome, thank you, Paul. Go ahead, please.
So for step 2, set the output from the function generator to 5 volts peak at 100 hertz. Make sure the AC coupling for channel 1 has been selected.
Okay, so AC coupling on the oscilloscope, it is on. So, okay, now, can somebody convert 5 volts peak into RMS so I can set it directly from the multimeter? So if you have RMS, sorry, if you have peak, you only need to multiply that amount by the magic number.
Yeah, it's 3.5 for how many? What do you want? 3.535.
Okay. So if you take a look to the multimeter, let me put it on the spotlight. The multimeter right now is showing you 3.53 volts RMS, which is equal to 5 volts peak. Now I'm gonna spotlight the oscilloscope, and as you can see there, the peak of our sine wave coincides with the with the first division, which is equal to 5 volts. So we have the proper amplitude. And what is the frequency that we need?
$100.
100 hertz. Now I'm gonna press the frequency button on the multimeter, and using the function generator, I'm gonna change that to 100 hertz. So right now we are at 93. And that's it. So we have 100 hertz for frequency, and we have 5 volts peak, or 3.53 volts RMS. So it is properly set. Let's take a look to the oscilloscope. What do you think I need to adjust on the oscilloscope to have a better picture of the sine wave? Because right now, I cannot even see one full cycle. I have two options.
You need to adjust the horizontal scale.
I need to use the horizontal scale or the time scale. So I need to make it bigger, okay? So now we're back in business. Let me see if I can find a better angle to show you the oscilloscope. Okay, silly webcam, but let me see if I can move it a little bit. No. Either way, I'm gonna read it out loud. So right now, one of the options was to modify the horizontal scale, but also we can use the auto set function. I just clicked it, and it does for you as well. And when you use the auto set function, you can also have different properties shown on the screen. So at this point, we are good to go. We are ready for step number 3. If you would like to continue, Paul, please.
Vary the output frequency from 100 hertz to approximately 1 megahertz in 10 to 15 steps. At each frequency setting, record the voltage on the oscilloscope and on the digital multimeter.
Great. So right now, I'm going to open up a spreadsheet. And I'm going to share it. Okay. So on the first column, I'm going to have my frequency in hertz. On the second column, I'm going to have the voltage input, the one coming from which instrument is this one coming from?
Oscilloscope.
Oscilloscope. Okay. So the first column is going to be adjusted by the function generator. The second column, oscilloscope. Third one, by elimination, multimeter. And what is the quantitative definition that we are reading of the multimeter?
Voltage output.
And what are the units of that voltage output?
VO.
It will be the voltage output, VO, but what is the quantity? Do you get voltage peak to peak? Do you get voltage peak? What do you get from the multimeter?
Voltage RMS.
Voltage RMS. We have to be super careful because right now, the way we have defined our columns, if we perform the ratio between output and the input, that will be an incorrect ratio. You have to make sure that the input or the output, they have the same units, so to speak. So we're gonna, the raw data is gonna be the voltage input in peak, because that's what we're gonna be reading from the oscilloscope. And then also we're gonna be reading voltage output in RMS from the multimeter. Okay, so we're gonna start, the first frequency that we're gonna set is 10,000. Then we're gonna jump all the way to 100,000. And we're gonna be increasing that by the same amount till we reach 1 million hertz. Okay, now our table is set for us to collect data. Okay. Let me add one more column here, which is going to be peak to peak. Because every time that we can get that voltage peak to peak reading directly from the oscilloscope. Okay. So now let's set up the spreadsheet without knowing the values of the voltage peak to peak coming from the oscilloscope. So when you want to do that, even if you don't have the values yet, you can just select the cell. And how do we convert voltage peak to peak into voltage peak?
You divide by 2.
Perfect. Divided by 2. Right now it's 0, and I'm just gonna fill out the entire column with that formula. Okay. How do we convert voltage peak into voltage RMS?
multiply it by 0.707.
Voltage peaks times the magic number 0.707. And we're just gonna fill out those values there. Okay, now the empty columns are gonna be filled out by the data that we're gonna measure from the experiment. Are we good to go? Do you need more time looking at the spreadsheet? Please let me know.
Just a quick more minute with the spreadsheet, please.
Okay.
You're good.
Thank you. I'm ready whenever you guys tell me to go back. Are we ready to start collecting data?
I'm all set.
I'm good to go.
Awesome. If I can see a couple of yeses on the chat, please. Thank you, Luisa. Okay, so now I'm gonna stop sharing the spreadsheet, and we're gonna go back to the instruments. Because the oscilloscope has a way higher usable frequency range. It's around 2 megahertz, spoiler alert, but we are not focusing on calculating that. The oscilloscope is our reference. What we need to find out is the multimeter's cutoff frequency. So we're gonna be focusing more on the multimeter. Okay. So at this point we have 100 hertz, but the first data point that we want to collect is 10,000 hertz. So I'm going to increase the frequency. So if you take a look to the multimeter, right now what you see is the amplitude. I'm gonna switch it to frequency, and it says 123 hertz. I'm gonna switch it to 10,000. So I'm gonna go up by 2 orders of magnitude, and I'm gonna multiply that frequency to reach 10,000. Okay, let's assume that's 10,000. If you see the oscilloscope you can see that now the signal has changed. Therefore, we have to change the parameters on the oscilloscope. And for that, I'm just gonna auto set it. It's gonna calculate the new values. And then we have again a steady signal. Okay, so I'm gonna read out loud the voltage peak for the voltage peak to peak for the oscilloscope. That's gonna be 10.4 volts. And for the multimeter in RMS, we're gonna have 3.56 volts RMS. So again, for the oscilloscope, we have 10.4. And from the oscilloscope, we have 3.56 from the multimeter. So we have the first row. Now, let's go all the way to 100,000 hertz. So take a look to the multimeter. And now I'm gonna switch to the next order of magnitude. 100,000. I'm gonna check the frequency. Right now we are at 98, 99 kilohertz. I'm gonna increase it just by a notch. Okay. I'm gonna do the auto set on the oscilloscope again. Okay. And let me check the voltage. So here we go. For the second row at 100,000 hertz, we have a voltage peak to peak of 10.3. And we have a voltage output on the multimeter of 3.48. Guys, am I going too fast?
No, you're fine.
Okay,
Yep, you're good.
cool. Now we are gonna continue filling out the row, but now I'm gonna go back to the function generator and increase the frequency to 200,000. I'm gonna check the frequency. I'm gonna increase
Sorry,
it
what
to
was the voltage peak to peak on that one?
10.3.
Thank you.
Yep. Increasing the frequency the other way. So if you take a look to the oscilloscope, the signal is being shortened, which means the period is decreasing. If the period decreases, the frequency goes up. Okay, let's assume this is 200,000. And let's measure voltage. Let's start with the oscilloscope. The oscilloscope is at 10 volts peak to peak. The multimeter is at 3.25, 3.25 volts RMS. Gonna go back to the function generator and crank up the frequency to 300,000. So if you take a look to the oscilloscope, you're gonna see again that more cycles can be displayed. Okay, so right now we are at 300,000. The oscilloscope is showing 10 volts peak to peak. And the multimeter is showing you 2.98 volts RMS. Okay, let's continue. Gonna increase the frequency to 400,000. 400,000. Okay, so if you take a look to the multimeter, you can see that it's blinking. It's having a higher time calculating the voltage RMS, but I can see a constant number, and that's the one that we're gonna take. But let's do column B. For the oscilloscope, voltage peak to peak, we have 10 volts. For the multimeter voltage RMS, we have 2.72. Let's move on to the next frequency, 500,000. Okay, 500,000. So for the oscilloscope, peak to peak, we have 9.84 volts peak to peak. And for the multimeter, we have 2.92. Okay, let's continue. Let's go to 600,000. So if you take a look to the oscilloscope, you're gonna see more cycles even. As we increase the frequency, we are seeing more cycles. The frequency is telling you how many times a cycle repeats itself in 1 second. I'm gonna say that again. The frequency tells you how many times the cycle of that sine wave repeats itself in 1 second. Okay, so right now, because we are a super high frequency, 600,000, this sine wave, if we plot it in 1 second, is gonna repeat itself 600,000 times. In comparison, if you go all the way to a sine wave of 1 hertz, that sine wave at 1 hertz only repeats itself 1 time in 1 second. Okay, so let's continue. Voltage peak to peak from the oscilloscope is equal to 9.68. 9.68. And the voltage output in RMS is 2.53. Let's continue. I'm going to increase the frequency to the next level, 700,000. Okay. Now, voltage peak to peak is 9.60. and voltage RMS from the multimeter, 2.11. Next frequency, 800,000. Okay. Voltage peak to peak from the oscilloscope is 9.36. Voltage RMS from the multimeter, 1.71. The second to last value at 900 hertz, 900,000 hertz. Okay. Peak to peak is 9.28. RMS voltage from the multimeter, 1.34. Last data point at 1 megahertz. One megahertz. We have voltage peak to peak, 9.12. And multimeter, 1.04. Mark, for 700 kilohertz, the peak to peak was 9.6. And for 900 kilohertz was 9.28. You're welcome. And with that, we conclude assignment number 4. Okay, so we're really close to the end. 200,000, Ryan, that was 10 volts peak to peak. Okay, so now on that same spreadsheet, you're gonna generate another tab. The first tab, you can call it, I'm gonna call it A4, just for assignment 4. Okay, on the second tab, let me share my spreadsheet. On the second tab, I'm gonna call it A5. Okay, right there. And before we set up that spreadsheet, I'm gonna show you the configuration that we're gonna have for assignment 5. Okay, so we're gonna start at the function generator. Okay, I am drawing with the mouse because this computer doesn't have a touch screen. That wouldn't make much of a difference anyway, but whatever. So from the function generator, you can see this at the first arrow coming down here. One cable is gonna be connected to the input of our filter, okay? Then the filter signal coming from the output down here is gonna be connected to the multimeter. That multimeter is gonna have the filtered signal, Okay, that's gonna be our VO, or voltage output. Let's come back to the function generator. The function generator is gonna have another cable that will bypass the filter and go straight into channel number 1 on the oscilloscope. What we see, the display on the oscilloscope is gonna give us our unfiltered signal or voltage input. Okay, so that's the flow. Let's go back to the spreadsheet. So the function generator and again, it's gonna be the same amplitude. We're gonna keep it the same. Function generator, this time the frequency is gonna change from, and we're gonna start at 100 hertz. Then we're gonna go to 500, 1,000, 1,500, 2,000, 250. Okay, so that's our first column. The oscilloscope is gonna be our voltage input. Again, voltage peak to peak. And the multimeter is gonna be our voltage output in volts RMS. Okay, so we're gonna read the oscilloscope, which is gonna be our unfiltered. And the multimeter will measure the filtered signal. Oops.
I'm assuming we still have to calculate the oscilloscope value into VRMS to actually compare.
That is correct. Yeah, we did it before. That's why I am not doing it here again.
Okay.
Okay, but that is correct. You have to have the quantity in the same characteristic in order to correctly calculate the gain or the ratio between the output and the input. Now, let's go back to the experiment. So right now, you should be able to see the pyramid. I'm gonna connect. So we have, I'm just gonna follow what we saw on the slide. The filter signal is gonna be connected to the filter signal is gonna be connected to the function generator. Okay. Need another cable. So filter signal to the multimeter. And unfiltered signal to the oscilloscope. Okay. Now we have the proper cabling. And who would like to help me with the steps for assignment 5? This is the last one, okay? Who will be kind enough?
I can do it again if you want.
If everybody's okay with that, I'm okay with that too. And okay, yeah, go ahead, please.
Turn on the filter and make sure channel is set to 1. Type in 2000 and press FREQ. The screen under cutoff frequency should read 2, and the freak and kilo button should be lit. Note that 2 kilohertz was set as the cutoff frequency for the filter because it is known from assignment 4 that the 3 dB down point of the multimeter is much higher than 2 kilohertz. This will limit the effects of the roll-off in the measurements caused by the multimeter.
Okay. Step 3, please. Could you continue with the step 3?
Oh, sorry. Vary
Okay.
the output frequency from 100 hertz to approximately 5 kilohertz in 10 to 15 steps. At each frequency setting, record the voltage on the oscilloscope, VI, and on the digital multimeter, VO.
Okie doke. So the only thing that we need to make sure is that the unfiltered signal, it is 5 volts peak. Okay. Which we are at that because that was the same magnitude that we had for the previous assignment because we never changed the output level from the function generator. Okay. I'm just gonna decrease it to 5.3 to get closer to what we should have. Okay. So if you see on the multimeter a voltage RMS of 3.53 is because we have a voltage peak of 5 volts. Okay. So we have at the bottom of the pyramid, you can see 2000 or 2.0. And the 2 buttons which are lit is the kilo and the freak button. So right now, everything is set for us to start making measurements. We need to start at 100 hertz. Those are 100 hertz. Okay. I'm gonna leave it to magnitude and let's start collecting data. The first row goes like this. Voltage peak to peak from the oscilloscope is equal to 10.2. Voltage output from the multimeter, 3.53. Can I increase the frequency now?
Yep.
Thank you. Now I'm gonna go from 100 hertz to 500. Okay. Voltage peak to peak from oscilloscope, 10.4. Voltage output from multimeter, 3.56. 3.56. Let's go to 1000 hertz. Function generator. Let's increase the frequency. Right now, the way I am adjusting the frequency, I am seeing it from the oscilloscope, okay? If you wonder. Cool. So right now we are at 1,000 hertz. So peak to peak from oscilloscope, 10.4. RMS from multimeter, 3.53. Let's go to 1,500 hertz. I'm just gonna auto set the oscilloscope, and I'm gonna keep increasing the frequency. 1.5 kilohertz. There we go. Okay, peak to peak is equal to 10.3. Voltage RMS, 3.39. 3.39. Let's do 2,000. 2,000 hertz. Okay, 2,000 hertz. Peak to peak is 10.3 from the oscilloscope, and from the multimeter we have 2.58. Let's go to the next one, 2,500. There we go. 2,500. We have peak to peak from the oscilloscope, 10.4. RMS from multimeter, 135. 1.35. Okay. Let's increase that to 3,000. I need to go all the way to the next one. Decrease this guy. So we need 3,000. Gonna readjust the oscilloscope. Okay. Let's take the measurement. From the oscilloscope, we have 10.4 peak to peak. From the multimeter, we have 0.63. 0.63. Let's go to 3,500. Adjusting it from the function generator. Cool. 3,500 hertz, and we have peak to peak of 10.4 and RMS of 0.37. Again, peak to peak 10.4, RMS 0.37. Let's do 4,000. And from the oscilloscope, we have 10.4 peak to peak. And from the multimeter, we have 0.21 volts RMS. Again, from multimeter, 0.21 RMS, volts RMS. If you take a look to the multimeter, you see 212, but that's millivolts, okay? Now let's do 4500, second to last. Okay. From oscilloscope, we have, can somebody guess how much do we have from the oscilloscope?
10.4.
10.4, ding, 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 ding. And from the RMS, we have 0.13. We're just using two significant digits, okay? 0.13 from the multimeter. And finally, 5,000 hertz. Okay. Because the oscilloscope has the unfiltered signal, it doesn't matter if we increase the frequency, it's going to remain being the same peak to peak. That signal from the oscilloscope is unaffected by the filter. So again, peak to peak from oscilloscope, 10.4. And from the multimeter, we have 0.08 volts RMS.
Did you tell me what the values were for 100 hertz? I didn't catch them.
Sure. For 100, 3.5. From the multimeter, right? Or both values?
Both values, but I could assume that it was 10.4 for the.
Right, for the oscilloscope, correct. Any other questions?
Do you, I just noticed that for two of them, the oscilloscope dropped down to 10.3. Do we have any reasoning for that, or is that just like equipment?
It's just part of the equipment, yeah. Theory-based, obviously it would have to be 10.4, but let's say maybe we don't have like the most, like the top-notch cables. Maybe the way the parameter is set up is affecting like all the electromagnetic fields created by the instruments. Maybe they're affecting each other. You know what I mean?
Yeah.
We just need to be aware of what we're doing. And if it were something, a bigger difference than that, then we will be worried about that. Okay, so that's the end of assignment number 4. Okay, so with all that data, you are gonna you will have to tackle the questions on the post lab analysis. And when you start working on that, there might be questions. Okay, don't forget to shoot me an email to do that. Or if your data is not making any sense, we could set up a Zoom meeting and we can discuss it together. But at this point, this is the end of the experiment. Okay.
So so because this was technically experiment number 2, I know you gave us the worksheet for experiment number 1. So is experiment, ideally we should have experiment number 1 done by tonight, and then we should have this done by 3 days from now.
Ideally, correct. Yes. nothing will be marked as late. But again, that's the ruler that lets you know how you're doing pace wise in the course with regarding the deadlines.
And I noticed that you put up a pre-lab for experiment 1, like submission area. Are you going to put up one for experiment 2 and like the other experiments in the future, or are those like just to hand them in, or like are they due before lab or anything like that?
I'm gonna do those the same way it is set up for lab number 1. I'm gonna set it for the other labs as well.
Okay.
So those are just drop boxes for each item. Okay.
Okay.
It's just I haven't set those up, but I will.
Alrighty.
Okay. So I'm gonna stop the recording.